going to try solving a problem and match an impedance using a quarter wavelength with the help of a Smith chart. Here is an example of a Smith chart. Now let's read the problem. A 50 ohms transmission line is terminated with a load having an impedance of 40 minus J30. We know that the ZL, or the impedance of the load, is 40 minus 30, and our ZO is equals to 50 ohms. The first step that we're going to do is to normalize this value. To normalize this value is we need to divide the ZL over the ZO, which is equals to the 40 minus J30 over 50 ohms, resulting to a normalized value of 0.8 minus 0.6 J. Now let's try this problem. Use the Smith chart to find the distance in wavelength from the load to the closest place at which a quarter transformer could be used to match the line. Since we have a normalized value, we're going to plot it to the Smith chart, where here the 0.8 is your real value. As you can see here is the 0.8 mark, and negative 0.6 for the imaginary value. The imaginary value is below our x-axis since it has a negative value. So 0.8 is right here and 0.6 is right here. Then we're going to match their midpoint where it is, and here it is. After that, we're going to create a straight line through it. Okay. Then the second step is to create, after finding the point here, the midpoint of the real and the imaginary value, is to create a SWR circle, where the resistive part is going to be on the right side, your SWR. To confirm this value, that this is right, we could try solving for the tau, which is ZO minus ZL over ZO plus ZL. Then this value will give us a result of 0.33, and it has an angle of 90 degrees. This is already in a polar form. The next equation that we'll be using is SWR is equals to 1 plus 0.33 over 1 minus 0.33, and that will be equal to 1.985. So that's the value of the real in the SWR circle. As you can see here, our computed value is almost the same as the circle hit the x-axis around here. Then, going back to the problem, is that after we extend the point A here and found its wavelength 0.376, we're going to look for the place where its resistive value is much more closer. And since it's quite in the middle, but there's a bit significance to the left compared to the right, so we're going to use the left side, and the left side value has a 0.5. After finding these 2 points, To solve for the distance, we just need to minus the 0.5 and the 0.376. Resulting to a distance of 0.124 in wavelength. Now let's try another problem. Now here, B. Find the characteristic impedance that should be used for the quarter wave transformer. Now the formula for that is Zin, and the part where the SWR circle is near with our Zin, and that is approximately 0.52, as you can see here. So the formula will be 0.52 multiplied, since this value is already normalized, we need to multiply it with our Z out, T 50 ohms, resulting to 826 ohms. Now the Z prime out, or the main impedance in unnormalized value, have a formula of the result of our Z in times the 50 ohms, resulting to a 36.05 ohms right here. Now for the last problem, let's try in finding the length of the transformer given that the operating frequency is 10 megahertz and the velocity factor is 0.83. Now the formula for that problem is the lambda. Since it's in meters, we're going to use the meter. It will automatically be 300 as a basis for the meter, multiplied by the 10 megahertz and and multiplied by the velocity factor, which is 0.83, resulting to 824.4 meters. Now since this is a quarter wavelength, quarter means 4. So for the length, we need to divide the lambda by 4, resulting to a 6.1 meters. And that's all there is. And here is the proper graph of our quarter wavelength. Thank you for watching.